Okay, so this is section 10.5, angle relationships in circles. And in this section, we're going to talk a little bit about what happens when we have lines that intersect with a circle. And as you'll kind of find out, there's three ways that this could happen when we have lines that are intersecting with circles. It's possible for them to intersect on the circle, outside the circle, or inside the circle. Those are the three possible ways that the two lines could intersect. And these first three theorems right here, this 1, 2, and 3, are going to talk about those three instances. So this first one, the tangent and intersected chord theorem, it says if a tangent and a chord intersect at a point on a circle, so I'm going to circle that for us, on a circle, then the measure of each angle formed is 1/2 the measure of its intercepted arc. So what that's saying is, when we have these two lines that intersected right here, this one is a tangent and a chord, if we wanted to find angle 1 right here, angle 1 would be equal to 1/2 of this arc right here. So if we knew the measure of that arc AB, we could take 1/2 of that and we would find the measure of angle 1. And similarly, if we wanted to find angle 2, we could just take 1/2 of the arc ACB, the major arc ACB on the outside. So that is if it's on a circle. So that was like example 1 right here. This next one would be if it's inside. And I got my order a little bit messed up. This would technically be like number 3 on ours. So if two chords intersect inside a circle, then the measure of each angle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So what that's saying is, if I wanted to find angle 1, if I wanted to find angle 1, then what I would do is I would add this arc and this arc, so I would add DC and AB, and then divide by 2, and that would give me the measure of angle 1. Similarly, if I wanted to find the measure of angle 2, I could add AD and BC going this way, add those and divide by 2, and I would find the measure of angle 2. Okay, so let's do this, goes inside. Okay, now the last one was if the lines intersect outside of the circle. And this says if a tangent and a secant, two tangents or two secants intersect outside a circle, then the measure of the angle formed is 1/2 the difference of the measures of the intercepted arcs. So on the one above this, you would add them and divide by 2. In this instance, you would subtract and then divide by 2. So for example, if I wanted to find angle 1 right here, then I would add this measure and subtract this measure, and then divide by 2. And that would give me angle 1. Or if I wanted to find angle 2, I would subtract this angle measure minus that angle measure and divide by 2. So the big thing on this one is you're going to do big minus small divided by 2 is going to be equal to that outside angle. Okay, and then the last theorem talks about circumscribed angles, and it says right here in this core concept, a circumscribed angle is an angle whose sides are tangent to a circle. So this right here is considered a circumscribed angle. Okay, and then the theorem says the measure of a circumscribed angle is 180 minus the measure of the central angle that intercepts the same arc. So, for instance, what this is saying is if I want to find the measure of ADB, so this circumscribed angle right here, what I can do is 180 degrees minus this degree measure right here. So 180 minus that ACB is going to give me the circumscribed angle. Okay, so there's a lot of vocabulary words that are being used in these four theorems, but it's actually a little bit easier to step back and look at more how the formulas are set up rather than try to remember all of the vocabulary words, because there are a lot of them. Looking here at number 1, we'll start to work some of these examples here. It says line M is tangent to the circle. Find the measure of the red angle or arc. Okay, so here for A, we'll notice that the angle 1 is right here. Okay, and we're going to be able to use that first theorem that we talked about, the tangent and intersected chord theorem, which says that this angle 1, so angle 1 is equal to 130 degrees divided by 2. So if we do 130 degrees divided by 2, that would give us 65 degrees. So that means that angle 1 is 65 degrees. Similarly, for B, if we needed to find this major arc right here, we would kind of be working backwards. We would say that the measure of KJL would be equal to 125 times 2. So it's kind of working backwards. You could also think of it as this KJL divided by 2 is equal to 125, and then you would multiply by 2 on both sides. You could also think of it like that. Either way works. I'm just going to write it as times by 2, which means that this red arc is going to be equal to 250 degrees. Okay, so not too bad. As we move down here and start to apply some of the other theorems, this one wants us to find the value of x. So this is going to be the one where the two lines, these two chords, are intersecting inside of the circle. So this one says that I'm going to add that x is going to be equal to 156 plus 130 divided by 2. So if I simplify that, 156 plus 130 is 286. So 286 divided by 2, and 286 divided by 2 gives us 143 degrees. Okay, so that was for A. So that would mean that angle X is 143 degrees. Okay, so for B, it wants us to find X again, but this time, this is where they are intersecting outside of the circle, so we're going to need to use the third theorem that we talked about. The third theorem being the angles outside the circle theorem. So this one says that I'm going to take the biggest one, which is 178, subtract it from the smaller one, which is 76, and then divide that by 2, and that would give me the value of x. Okay, so 178 minus 76 is going to be 102. So then if you do 102 divided by 2 is equal to x, which means that x is equal to 51 degrees. Okay, so that would mean that this angle right there on the outside, x is going to be 51 degrees. Okay, now here's some other examples that you could try. I think, actually maybe we'll do these ones together. I think these will probably be good ones to practice together. But the answers are right here, so we can, make sure that we get to the right spot. For these, for number 4, notice that it's giving us this angle right here, which is not actually the angle that we can use right now for our theorem. So we know that this angle, this blue angle, is 102, which means that its vertical angle over here is also 102. So if we add those two together, that gives us 204 degrees. Well, we also know that this whole thing right here should be 360 degrees. So if we do 360 minus 204, that would give us 156 degrees. So that would mean that, let's do a different color, that this green one plus this green one would be 156 degrees. And we know that those two angles are the same because they're vertical angles, so I could divide it in half to figure out what each one is. So 156 divided by 2 should give me, what's that? 78. So that would mean that the green angle is 78 degrees. So now I can apply the theorem. I can do that 95 plus y divided by 2 is going to be equal to 78 degrees. Okay, so I'm going to have to multiply by 2 on each side. So now we're going to get 95 plus y is equal to 156. And then I subtract 95, and we get that y is equal to 61 degrees, which is what it gives us as the answer. Okay, so we had to work backwards a little bit on that one. And same thing here on number 5, we're going to have to work backwards a little bit. This is talking about a circumscribed angle, so one that's on the outside. And if we set that up, normally it says that we can do big minus small divided by 2 is the one on the outside. So instead of knowing the bigger angle, we're just going to name it A. So A minus 44 divided by 2 is going to be equal to 30 degrees. So if we're going to solve for A, we're going to have to multiply by 2. So A minus 44 is equal to 60. And then when we add 44 to the other side, we're going to get A is equal to 104 degrees. Okay. Moving on down here, now we're going to apply the last theorem that we talked about, the fourth one. That is the circumscribed angle theorem. And that one, just as a review, says that the measure of a circumscribed angle is equal to 180 degrees minus the measure of the central angle that intercepts the same arc. So looking here at A, it's going to give us that this ADB, or right here where X is, so X is going to be equal to 180 degrees minus 135 degrees. So when we simplify that, we're going to be given that X is equal to 45. So that means this right here is 45 degrees. So not too bad. Here for B is where it gets just slightly more complicated, because notice that this X right here is different than this 135 right here. So if we were to connect E, G, F and find that angle, that would be the same type of angle as this 135 degrees. But this X here is a little bit different because it's connected on the outside, touching on the circle. So we're actually going to have to go back and use a theorem that we learned in section 10.4. And that section, or that theorem, is called the measure of an inscribed angle theorem. It's theorem 10.10, and that's on page 554. So if you need to go look that up, I'll write that right here. Page 554 is the theorem. Okay, so we're going to have to actually use that theorem, the inscribed angle theorem, and the circumscribed angle theorem to figure this out. So in order to do that, we're going to first write that we know that EJF, so angle X, is going to be equal to 1/2 of EF, which is right here. Okay. The reason why we know that is because of that theorem that's on page 554, which again, that one is called the measure of an inscribed angle theorem. So now, we also know that this EF right here, it, by the definition of a minor arc, because that's what that is, that's a minor arc, we can use that and the circumscribed angle theorem to substitute this part with 180 degrees minus EHF, which is this part right here. Okay, that's applying the circumscribed angle theorem, because we're going to do that this right here, we know that is the same as EF. And then that theorem says we can do 180 minus 30. So if we just bring this all down, we're going to have x is equal to 1/2 times 180 minus 30, which means that x is equal to 180 minus 30 is 150. And then if you divide that in half, you get 75. So that would mean that x is 75 degrees. Okay, so that one's a little bit complicated. We're going to do another example like that here in a moment so we can get 2 chances to kind of see how that works. But once you do a couple problems like that, it becomes pretty quick. You see it a lot easier. But the first time it is pretty tough. Here for number 4, again, it's similar to what we were doing here in number 3, so I'll keep them in the screen. So it says find the value of x. So in order to find the value of x, again, we're going to use that circumscribed angle theorem. And we know that this x should be equal to 180 minus 120, which means that x is going to be equal to 60 degrees. Okay, and so that's another one that was very similar to this problem right here. When it's given to us as we want the circumscribed angle and we're given this angle right here, it's really easy. We're just doing 180 minus that number. But here on this next one, we'll see that this one is like B, where x is this angle over here. It's not the circumscribed angle. But notice what we did last time. In order to solve for x, we were able to do 1/2 of 180 minus the circumscribed angle. So because we did it correctly up here at B, we can kind of skip some steps to use it on number 7. We don't have to go back and think through the whole theorem. We can just say, oh yeah, I know that it's going to be 1/2 of 180 minus the circumscribed angle. So if we do 180 minus 50, that gives us 130. And then if we divide that in half, that would give us that x is equal to 65 degrees. Okay, and that's the essence of the chapter. This is your homework right here. If you have any questions,